We're going to continue our work in linear algebra, and this second week is going to be a little more abstract than the first. We're going to concentrate a lot on proofs and things of this sort. So we're going to go back this first and the second sections we're going to cover are going to be a little bit of a review of things that you've already done, except we're going to pay maybe a little more careful attention to definitions and terms. So to start off with, I'm going to define a Cartesian product. And one of the new features I also want to emphasize is that any material that I consider testable, I'm going to make the heading an orange color. And part of this is because there are a lot of things that I want you to see, but you're not necessarily going to be responsible for on the exam. They're more for enrichment. They're important, but we just don't have time for you to learn everything in so much depth that I could test you on everything, but yet they are important. So Cartesian product is something that we wanted to know for the exam. It's in orange. And basically, we're going to start off talking about the Cartesian product of two sets. So we're going to consider two non-empty sets, A and B, and we're going to define the Cartesian product of those two sets, which is denoted as A with an X between them, B. And this is not multiplication, okay? So the context should make it clear that we can't multiply sets. This is a Cartesian product. And it's going to be defined as the set of all ordered pairs x, y, such that x comes from A and y comes from B. Okay, notice the ordered pair. The first element comes from the first set in the Cartesian product. The second element in the ordered pair comes from the second set. And we'll do a really quick example. We use these a lot in analysis. We use it in probability theory. Suppose, for example, we let A be the outcomes from flipping one coin. So A is the set of heads and tails, right? And B will be the outcomes from tossing one die. Okay, so B is the set of 1 through 6 natural numbers. And if we look at the Cartesian product of A and B, we can see that it's going to be heads 1, heads 2, all the way up to head 6, then tails 1, tails 2, all the way up to tails 6. Okay? Now, one thing you want to be careful about is that the Cartesian products are not commutative. And as a quick exercise, try to construct a Cartesian product of B with A. You'll see it's not the same as a Cartesian product of A with B. Okay? Now, very often we want to consider more than just one set. We want to take the Cartesian product of a finite number of sets, and it's really just an extension of this definition. It just says that the Cartesian product of sets A1 through AN are all the ordered n tuples such that the ith component comes from AI. All right? Okay, so now let's go ahead and talk about vector spaces. We've never actually defined what this is. So we're going to say that this is some non-empty set V along with a field F that has two operations associated with them. And I want to mention really quick what a field is. A field is a set of numbers that has a certain set of properties, and we're not going to go into what those are. That's a whole discussion in and of itself. But what I want to mention is the fact that the two fields that we're going to use are either going to be the real numbers or the complex. Okay, those are the two fields that are most of interest to us. And these two operations I'm going to call plus with a circle around it, and I'm going to call a multiplication sign with a circle around it. So addition maps two elements in the vector space to another element in the vector space, and the multiplication maps a vector and a scalar, okay, some element from the field, into a vector. Okay, and this can be very general. This plus and this multiplication do not have to be the standard sort of addition and multiplication that we have in mind. However, they do have to satisfy 11 conditions, which I'm going to state briefly. The first 5 conditions have to do with addition. It says that V is closed under addition. And again, to kind of make sense of this, just go back to what you know about vectors. Closed under addition means if you add two vectors, you get another vector, right? Addition is both commutative and associative. In other words, commutative means that u plus v is the same as v plus u. We know that we can do vector addition either way, right? Doesn't matter the order in which we add vectors. And associative means if we have three or more vectors being added, we can group them in any way we want, okay? Now, there's also this thing called an additive identity element, which we're going to call the zero vector. It's going to be zero with a bold face. And this is the vector such that for every vector in capital V, when that vector is added to zero, we get back the vector. Okay. All right. The last is that for every element in V, there's an additive inverse, meaning that for every vector, there's another vector we can add to it that will give us the zero vector. Okay? The next couple of conditions deal with multiplication. And they say that V is closed under scalar multiplication. And again, if we multiply a scalar times a vector, we get back a vector. That's what that statement means. The quote-unquote multiplication is also commutative and associative. In other words, it doesn't matter if we put the scalar before or after the vector when we're doing the multiplication. And if there's more than one, we can multiply them and group them however we want. Okay. And last, there's a multiplicative identity element in F, which is just always 1. So this is saying that 1 times any vector gives us back that vector. All right. And the last two laws are just distributive laws. The first is that the scalar can distribute over sums of vectors. Okay. And the next is that vectors distribute over sums of scalars. Normally we use the first law. We don't use the second law very much. If we have two scalars, we generally add them. Okay. And I'm going to drop the use of these kind of abstract symbols, but the reason why I use them is because the notion of vector spaces actually extends far beyond what we think of as a vector. So, we could have a Euclidean n space, which we call Rn. In other words, this is a vector that is the Cartesian product of R with itself n times. And that gives us the ordinary sort of vector that we're used to thinking about. But there are a lot of other vector spaces. For example, matrices form a vector space, if you think about it. And that's not surprising, right? Because a vector is just a special type of matrix. But they form their own vector spaces. Polynomials form a vector space. Infinite sequences. Okay, we can think of vectors as being finite sequences, but infinite sequences also form a vector space. And probably the most important is the notion of function spaces. It turns out that collections of functions, like continuous functions, for example, can actually form a sort of vector space. And we use this a lot. It's a very powerful fact in Fourier analysis, differential equations, integral equations, things of this sort. And so as we're going through these general concepts, it's a good idea to kind of keep them in mind because they're things that you're going to use over and over again. They're actually not just specific to vector analysis, but actually they're useful in a lot of other areas too. Okay, I want to talk briefly about what's called a norm. So a norm is just a function that gives the length of a vector. And it applies exclusively to vector spaces. And so I make this comment because some people get a norm confused with a metric. And a metric is a distance between 2 points, which is not necessarily the same as the length of a vector. Okay, so when we're talking about norms, we're only talking about vectors here. And we can define it as follows. We're going to define a norm on a vector space V, and we're going to use this symbol of double bars on both sides, and then whatever we want to take the norm will be that little dot there. Some people use absolute value signs, and I don't like that because we use absolute value signs with scalars. It has so many other contexts, so I'm going to use that double bar, which is a standard notation, by the way, but not used by everybody. And this function is going to map v into the reals. Okay, in other words, it maps the vectors into the reals, which makes sense because it's a length, right? So the output has to be a scalar. But it has to satisfy three properties. First, the norm of a vector can be 0 if and only if the vector is the 0 vector. That's an important fact. Secondly, if we multiply a vector times a scalar, its norm is equal to the absolute value of the scalar times the length of the vector, the norm of the vector. Okay. And this makes sense. This just says that if we multiply a vector times a scalar, the resulting length is the original vector times however much we multiplied it. The only difference is we have to note that this alpha can be from a field, so it can be complex too. It's not necessarily real. And last, we have what we call the triangle inequality. We say that the norm of a sum is less than or equal to the sum of the norms. And we can kind of verify this. We know that it's true in R2, right? We looked at examples where we have two vectors u and v. And we remember how we add vectors. We add them head to tail, right? So I can slide u up here, and this is the sum. And so in R2, you can actually show that this is true using the law of cosines, right? So you can show that this notion of a norm in R2 satisfies these three conditions. Okay. But again, the reason why I raise this point is because norms are also very general. Okay. We have what we normally think of as a norm, pardon the pun. We have the Euclidean norm, which just says that if I have some real vector, the norm is the sum of the square of the components. If we're in a complex space, it's basically the same thing, except now we're looking at the square of the modulus, right, of each component instead of the square of the component. And you can show that this satisfies the definition of a norm, except for the fact that the triangle inequality is not easy to prove. So this is a fact in mathematics known as Minkowski's inequality. And I'm not going to ask you to show that the Euclidean norm satisfies the definition of a norm. Minkowski's inequality is a little tricky. And while it's interesting, I'm not quite so sure I want to go into that much depth, okay? But one that you should be able to show as a norm, and it's not the Euclidean norm, is what we call the max norm, or the sup norm. And basically it says if we have a vector in Rn, okay, we're going to define the max norm, which is sometimes denoted by putting a little infinity down here as a subscript, is basically the maximum of the absolute values of all the components. Okay? And so basically what you do is you take a real vector, take the component with the largest magnitude, and that's the max norm or the sup norm. Okay, and you should be able to show that that in fact is a norm. Okay, the taxicab norm or the Manhattan norm is another one that you should be able to show. And basically it says if we have a vector in Rn, what we do is we take the components, take the absolute value, and we form this kind of like this path like this. Okay. And then the sum of those absolute values is known as the taxicab norm. Sometimes we denote it by a subscript 1. It means the L1 norm. Okay. And it's called taxicab because this is the distance that a taxicab would take, as opposed to, as the crow flies, right? As opposed to a vector like this. Okay. And these are very useful sometimes when we're working with matrices. Okay. All right, we're going to go on and look at inner products next now.